What's up everyone? In this video we're going to talk about Newton Fractals, and we're going to talk about how Newton Fractals work. We're going to implement Newton Fractals in Python, and obviously we're going to have to talk about Newton's method because that is what is used to make Newton Fractals. But before I go any further, I want to talk about 3 Blue 1 Brown's video on fractals, because if you don't know anything about fractals, I think that's a great place to start, and I would recommend you going on and checking that video out right after this video. Or just go right over there. Now, what the fuck even are fractals? Before we continue, we're going to have to talk about fractals. And fractals are objects that show the property of self-similarity. Now, what is self-similarity? Self-similarity means that an object is similarly equal, exact, to a part of itself. So, for example, I can talk about cock snowflake. And this is what a cock snowflake looks like. It starts with a triangle. And a triangle is made up of, obviously, 3 line segments that are equal to each other because it is an equilateral triangle. And on each of these line segments, I'm going to draw a triangle. So you can see how this triangle, the main one, the first one that we had, right, this one, is now made up of 3 more triangles. And each of these 3 new triangles can be made up of more triangles, right, wherever there is a line segment on the outer boundary. And so you can see that triangle has 2 more triangles, and so on and so forth. And you can imagine that I can go even deeper, but since I didn't write code for this, obviously I'm going to have to use Wikipedia for real animation. So you can see over here that you can really go really deep in here and start from a basic triangle, really. And I can show you another thing where if you zoom in, also from Wikipedia, you will continue to zoom in forever. That's the whole concept here, that fractals repeat themselves. The patterns repeat again and again. So that's what fractals are. And self-similarity is available in a lot of places. Obviously, you have probably seen this diagram or picture a lot, right, in computer science, the Mandelbrot set. And we also see self-similarity in nature. Right, so for example, this is Romanesco broccoli. And you can see the really like 3-dimensional type fractals in this, or self-similar objects in this broccoli. Obviously, it's pretty apparent. So what even are Newton fractals? So Newton fractals are these kind of fractals that appear out of solving for roots using the Newton's method. And we'll talk about how these are formed, because I think we have to talk about root finding and complex numbers a little bit before we go on and talk about how Newton fractals actually work. So that's what this video is about. Let's get right into it. So before I go any further, I want to talk about roots and complex numbers a little bit. And if you have a function, a root is basically telling you a value of x that sets the function's value equal to 0. So if I have a function f of x equals 2 of x, then it's clear that the value of the function is equal to 0, or when it crosses this x-axis, when the value of x is equal to 0, because if you multiply 2 with 0, obviously it's going to be 0. You can have 2x minus 2. If x's value is equal to 1, then 2x minus 2 will be equal to 0. And you can solve for this equation, 2x minus 2 equals 0, to get the root of any function. Now there's another thing that you probably might know, that the number of roots an equation has equals the degree of the equation or the function. So what is the degree of this function right here? Well, it's 1, because degree equals the maximum value of x. So if I say 2x squared plus 2, what is the degree of this function? Well, it's 2. Now you might say, where are all the other roots over here? I don't see any roots, because they don't cross the x-axis. And that's where the complex numbers come in the picture. So not all roots are real. Some roots may be complex, as we'll see further down the line. So let's say we have, if I set this to 2x minus 2, then clearly all the roots are obviously real, right? Both of these roots are on the real plane, and I can totally see that they cross this x-axis line. Clearly minus 1 and 1 are the roots. But if I just add plus over here, that's not the case, and you're going to have to do something else to find the roots. Anyway, so because if you try to solve for it, it will be equal to like -2 on the other side. And if you take the under root of -2, but because you want to get rid of the square, then it'll be under root -1, which is complex, which we'll talk about soon. So if I have a function x squared plus x plus 1, which is of this type ax squared plus bx plus c, then you can see that I don't know how to find the roots. Like normally, they don't cross this x-axis line. So that's where the complex numbers fit in the picture. And this is a quadratic equation, and we know a very simple formula for solving quadratics. So let's go right into it. Now to solve quadratics, this formula you probably might have heard before in your 5th grade probably. So minus b plus minus, under root b squared minus 4ac over 2a, right? So if you have a function ax squared plus bx plus c, you just put those coefficients in over here, and you get the solution for the quadratic. Now this only applies to quadratic because there will be more complicated functions. But let's say we solve this, x equals this, we get this as answer. Now the interesting thing here to notice is this -3 under root over here, because you cannot have this on the real plane. So you have to have another plane. Now you're entering the world of imaginary numbers. So we're just going to set this -1 in there, -1 under root to iota. And that's really what complex numbers are about. They're about these imaginary numbers. These -1 under root appear in a lot of places, from Schrodinger's equations to what have you. And that's what we're going to go into. So let's talk about these. So to represent a complex number, we need a real value, RE, and we need an imaginary value, IM. And the imaginary value is always going to have this, obviously, this constant, which will be 2 in this case. So that's what imaginary value constitutes of, an iota and a coefficient, which is a real number. So from the last example, if we want to represent the last solution, like this solution right here, these two solutions, this one solution, sorry, then I can represent these two numbers on the complex plane like this, where they have a real part and they have an imaginary part. And I can show where they exist on the complex plane. This is the complex plane. On the y-axis you have imaginary part, and on the real axis you have the real part. So what is the real part of this x1? Just take a guess. It's -0.5, which is probably here, right? And it's -0.5 for both of them. And what is the complex part for this? It's 0.866, which is almost here. So it's one value over here and one value over here. So that's really what complex numbers are about, and they're really interesting. You can represent any number really, like let's say x equals 3 4i or +2 + 4i, let's say. And of course then real part is 2, so real part goes to 2, which is here, I believe. And 4 is the imaginary part, so I could just put 4 over here somewhere. So that's where my number exists on the complex plane, and Newton fractals exist on the complex plane. Now before we go on to make a Newton fractal, we're going to have to learn about the Newton's method and how that is used to find these roots. So let's get right into it. So now let's talk about the Newton's method. And the Newton's method is an iterative method, meaning that the more you run the iterations of this method, the more better convergence you're going to get. So to get started, you need a starting value x0. It can be anywhere. Let's say it's here somewhere, right? This is x0, let's say. And given a starting value, we want to take the tangent value of the f of x, the value of the function at x0. Let's start with that. So that will be somewhere here, right? This is f of x0. F of x0. Now, what I need here is the tangent line of f of x0, at x0 basically. So what is the slope of this function at this point? That's what I'm looking for. And it probably is going to look something like this, right? Let me start again. All right, it's going to look something like this. And what I'm interested in here is the value at which, or the value of x, and this in the x-axis where this tangent line hits, which is x in this case. Let's call it x. I'm interested in this. And the Newton's method says that you can assume that this is the approximate root. Now you can run this method again and again, and this is where the iterative aspect comes into play. You can assume this x to be the new x0, or the starting point, and you can run this again, and you will find a new root, and you can see that it comes very close to the root. And if you start from here as well, you'll come very close to the true root, which is at this point. Let me color it up differently. So this is the true root, and it's going to get closer and closer with more iterations to this true root. Now I'm interested in this, in finding this x over here. How do I do that? So we know that slope of a function is rise over run, right? Slope of points. Now we're dealing with points over here, so let's write it up like that. This is the rise, right? And rise in this case is, let's call this y0. Rise in this case is y0 minus this thing right here, which is, well, 0, because the value of y on the x-axis obviously is going to be 0. And the run, which is this thing right here, is x0 minus x. And we're interested in finding x. So you can equate slope to rise over run, right? So you can say slope equals rise over run. And we know that slope of a function is also equal to the derivative of the function, the first derivative. So we're going to use that. So I've already prepared some equations, so we're going to look at them. We know the slope of the function equals rise over run, which is y2 minus y1 over x2 minus x1. Now you can continue and put y1 equal to 0, because y1 clearly is equal to 0 because x is on the x-axis, and on the x-axis value of y equals 0. And we're interested in finding this x. So let's write a better notation. Now we have a better notation. So x0 is the starting point, and y0 is the value of the function at this starting point. And this is the point where the tangent line hits 0, or on the x-axis. On the x-axis, the tangent line hits, but the value of the function is going to be 0 at that point, which is this. And we're going to equate it to the derivative of the function. Now, following this equation, we can solve for x, and we will end up with the Newton's method, which is equal to this. So this is what the Newton's method looks like, and let me erase some of this stuff that is much more clearer. So this is what Newton's method looks like, and you can run it iteratively. So if it's the first value, you get the second value, plug it in again, and you keep doing it again and again, as we said before, and you will converge to the root. You'll be very close to the true root. So that's what it ends up being. And you can do this again and again. So there are a few things that I want to talk about when it comes to the Newton's method. One of those things is that it depends very much on the starting value, where you start. If all of your starting values were in this part of the graph, or in these values of x, you would converge to this, because if you were here, you'll converge here to this root, and if you were here in this part of the graph, you would converge to this root. So it's very important to select the values of x wisely, I would say. And also, if the value of this thing right here goes to 0, then you got divide by 0. And it also makes sense intuitively, because if this is equal to 0, that means the slope of the function is 0, which is at this point right here. And if slope of the function is 0, then you're not moving anywhere. Where does this tangent line hit? It's parallel to the x-axis, so it's not going to hit anywhere. So that's really all there is to Newton's method. Now we're going to write Newton's method in Python, so let's get right into it. So now we're going to talk about the implementation of Newton's method using Python. First thing that I'm going to do is define this function over here that we talked about in the explanation. So f of x is going to return x squared minus 1. This is the function that we were talking about in the last explanation thing that we went through. Another thing that we do need alongside this function is the derivative of this function, and we can hard code it for now. F prime of x is the derivative in this case, is going to return 2x. Because the derivative of this thing right here, x squared minus 1, is 2x. If you apply the power rule, x squared becomes 2x and minus 1 becomes 0, so it's 2x. Now, let's apply the Newton's method on this f of x, and what we're going to do is we're going to start with a starting value over here, let's say starting value is 2, and we know Newton's method is this thing right here, x0 minus y0 over f prime of 0. So for I in range, let's say we run it for 10 iterations, x updates with x minus f of x divided by fp of x. And if we look at x, it's 1.0, which means that it converts to this root right here. Now if we started from the other side, it converts to the other root. So there's a problem here. We don't want to set manually which side we want to start from, so we have to solve this problem somehow. And one way to solve this problem, and I want to repeat the problem again, the problem is that we are manually giving starting points, and in reality, when we're talking about generic functions, we don't know what function we're dealing with. We want to have a space of x values or inputs. We want to have an input space where we check for each value of that input space where that input value converges to. So maybe I start here at, this value right here, minus 1.41, and that's my starting value. Where does this converge to? Well, it converges to minus 1 in this case. If we apply the Newton's method, we want to have a bunch of values that apply Newton's method on themselves and converge to some value. So maybe in this part of the graph, from 0 to minus 2, we have 10 values, and we converge. We apply Newton's method on each of those 10 values. So you can do something like x equals minus 2, x equals minus 1, x1 equals, x2 equals, x3 equals 0, or x4 equals 5, let's say. And we do this again and again for each of these values, but that's not very good. So what we can do is we can use NumPy. Let me import it somewhere else. And we can declare an array. Let's say np.array minus 1 or minus 2 minus 1.5 minus 1 0.25. Let's just go from here. 1, 1.5, and 2. And if we do this, hold up, it'll also work, and Newton's method will basically run for each of these values, and it'll update their own specific value in that location. So if I see x now, minus 2 converts to minus 1, minus 1.5 converts to minus 1, so on and so forth, and positive 1 converts to, positive 1, and 1.5 converts to 1. So far so good, but we can automate this even further using something called np.linspace, which takes in a starting value, minus 5, and an ending value. And it also takes a third parameter which says how many values do you want between minus 5 and 5. Let's say I want 10 values between minus 5 and 5. So I get this. These are the 10 values between minus 5 and 5, inclusive of minus 5 and 5. So I can use this instead of this np.array to construct this myself. And I get the similar x again with different values, so if minus 5 converges to minus 1 and any value in between converges to some root. Another thing that I can do here is I can turn this into a set, because you can see over here that many values converge to the same root. So I want to group this root into a single root. That's a single root all these values converge into, and the set will not have repeating values. It won't always work because these are approximate roots. They're not true roots. It just happens that in this case it does a very good job of converging. Now another thing that we can do here is we can talk about complex numbers. So let's talk about complex numbers. In Python, you can represent complex functions like this. J is what's used. So 1j is a complex number, and you can do 95 plus 1j. It's a complex number, and you can see the type of it. I think it'll also tell you that it's complex. So I can do the same thing to linear space. I can say 5 minus 5j to 10 plus 5 plus 5j. And it'll converge to the same thing. Now 0j is just telling me that there is nothing to the imaginary part of the complex number. So we only have the real component. So as I said before, that any real number can be represented by the complex numbers as well. So going on, we will be using these kinds of linear spaces. So let's go on further and try to find the true roots using NumPy, so we can use that as a reference instead of doing it like a monkey ourselves, like x squared minus 1. Okay, let's take the one on the other side. So let's use NumPy for some function to find the true roots. And I'm going to take some function like this, 3x cubed, plus x squared plus 2x plus 1. And it looks very straightforward, but there's only one real root. That's why it's exciting. It's kind of this random function I brewed up. So I want to apply Newton's method on this and see where we go, because obviously there are 3 roots and we are only seeing 1 over here. So there must be some complex roots and some real roots. So to do this with NumPy, you have to represent a polynomial using an array, basically. So to represent that using an array, you have to give different locations to different coefficients of the power, basically. That's what you're going to have to do. So in this case, the function is 3x squared, right? 3x squared and 3x cubed x squared plus 2x plus 1. Now this can be represented just like this in an array. 3, 2, 1, 2, and 1. Right? So this array now translates to a polynomial in and of itself. 3x cubed, and an easy way to start reading this obviously would be from the right side. So 1 plus 2x plus x squared plus 3x cubed. And I can do np.roots on this to find the roots of this thing. These are the roots of this thing right here. There are many complex ones, and there is one real one because there is 0j over here. Now let's try to solve this specific equation or function using our beloved Newton's method ourselves. So I'm going to do f1 of x here because this is a new function. It's 1 plus 2 multiplied by x plus x squared plus 3 multiplied by x. And that's my function, right? Cool so far. Now I'm going to make the derivative of this function f1p, and it's 9x squared from the, sorry, this is not correct, 3x cubed. 9x squared because 3x cubed, take the power rule, 3 comes in the beginning, and 3 minus 1 is 2. Plus 2 into x plus 2 and plus 0. So that's the derivative of this function. I hope I haven't messed anything up. Yeah. So let's try to apply this Newton's method over here and see what we get. So I have a linear space again from minus 5 to plus 5, and we have like 10 values. Let's say we increase that to 100, and we again do the same thing. Instead of f, we do f1, and we solve for x. And there are a lot of values here. Now what do I do with that even? So I'm going to turn it into a set so we have a better understanding. Now another thing that we can do is we can let it converge for more time. So let's run it for 100 iterations. You can see that there are more fine solutions to this, and we can run it probably for 1,000 more iterations. So now we have about 4 answers here, and actually there are only 3, and one of these answers are very close to each other. So for example, these two are almost identical. So we're going to consider these two as one solution, this one as a one solution, and this one as one solution. Now if you look closely, this one is very similar to this one. This one is very similar to this one right here. And this one with plus is very similar to this one. So you can see that it converged very well and was very close to this one. So that's all there is for implementing the Newton's method using Python and NumPy. Now we're actually going to implement Newton's fractal after all this time. So let's get right into it. So now we're going to talk about Newton fractals. And before we continue, I want to talk about imagining how Newton fractals are actually made. So you have a starting point and you have, S0, let's say, or x0, and you run Newton's method on it, and it ends up with a value of x that converges to approximately a root of that function. That is what we have talked about so far. Now, how does it relate to the Newton fractals? Really the same concept. What you do is you take a grid of values and think of it like a picture. A picture has a lot of pixels. So you can imagine these little boxes as pixels, kind of, right? Do imagine them like these little dotted boxes that you see. Like really imagine them like pixels. So, and in this case, a point, really. So let's say I take this point and I make this point using np.meshGrid. We will talk about that if you don't know that already. So if you have like 1, 2, 3, 4, if you have 8 boxes here, 8 boxes here, you'll end up with 64 boxes. And that's really what we're going for here. So out of these 64 points, if I choose this point and I run Newton's method on it, it'll converge to some root, right? Let's say a function has 3 roots. 3 roots, right? So depending on what root this point converges to, I'm going to color it that way. So let's say if any point converges to root 1, I'm going to color them blue. So if any point here converges to root 1, I'm going to color them blue. If any point converges to red root, or root 2 rather, I'm going to color them red. That's the concept here. That's it. There is nothing more to it. And if some point converges to root 3, I will color them yellow. That's it. That's all there is to it, really. So that's what we want to do here. And let's get right into it. All the concepts are the same. The only new thing here is the mesh grid part, how we make this mesh grid. Everything else is very trivial. So let's get right into it. So first thing that I want to show is this mesh grid. And let's make a mesh grid here. And it takes 2 arrays and it combines them together to make a grid. And you will see how that's done. If you just see plt.scatter xy, it takes values 1, 2, 3, 4, 1, 2, 3, 4, and takes values 1, 2, 3, 4, and it fixes them in an order to make this grid. It doesn't matter how it makes these grids, it turns them into these grids, and we can use them to do what we wanted to do, make Newton fractals. So let's get right into it. So first thing that I'm going to do is make functions, the function that we want to make Newton fractals of. So let's say f of x, and the function that I've chosen here is x cubed minus 1, and we can calculate the derivative of this function. It will be 3x squared because x cubed, so it's basic power rule. So it's 3x squared. Now the derivative of the function and the real function itself. So now we can continue. Now another thing we need here are the roots, the true roots, because we have to compare these approximate roots that our Newton's method has converged to and compare them with the true roots. And the one that matches or converges to, we're going to color them according to that. So let's get those roots. The method that we're going to use, we talked about it before, is np.roots, and we can define polynomials like this. So for example, x to the cube the third power has one polynomial, one coefficient. The power 2 has 0, power 1 has 0, and the power 0, which is the constant, has -1 as the coefficient. And these are our roots. And this will give us the roots that, well, NumPy thinks are the roots. And these are also numerically calculated. So, at least I believe that. So, and they can be off sometimes. Now, so I can store these roots, root 1, root 2, root 3. And I'm going to use them later to compare. Now let's make our own mesh grid. And to do that, we're going to have to make linear spaces first. So let's do that. And p.lin space. From -2 to 2, we're going to make a linear space. So for example, we're going to go from here to here. And we're going to go from here to here. And this is the piece of land we're going to use to draw Newton fractals, basically. These are the points, basically. And the resolution, we will define it beforehand. So let's say 300 is the resolution. And we're going to do the same for y. Now we're going to make a mesh grid, small xy, and p.meshGrid xy. And if we plt.scatter x and y, we end up with this. They're very close to each other, the values, because there's a lot of them. And that's our mesh grid. Now, we're going to continue and we're going to make our points. Now, these are not final points. These are x, y values. Remember that a complex number is made up of an imaginary and real value. I mean, we talked about that before. And we're going to use this y to be the coefficient for our imaginary part. So let's do that. So z will be our set of points, and it'll be equal to x plus 1j multiplied by y. And if you look at z, it is exactly that. So now we're gonna write our Newton's method for this, for I in range. Let's say we converge for, or we run the method for 100 iterations, and then z equals z minus f of z divided by fp of z. And we'll end up with some value of z. And you can see that some of these values have converged, it seems like, right? All these three values seem very equal to each other. So let's try to compare them. And to compare them, we're going to do this. We're going to have a threshold epsilon. And we're basically going to compare each of these values with these roots, all of them. And if the difference between them is close to 0, or at least approximately close to 0, which we're going to use this for, then we're going to color it with that color specifically. So let's do it. So Z1 is basically going to be a truth or true array or truth array, if that's what you want to call it. So we're going to take absolute value of Z minus root 1. And we're going to see if that value is greater than epsilon. Why greater than epsilon? Less than epsilon. Because we want to check, because these are approximate roots and they're not exactly going to be equal to 0. So if they're approximately in that range, then we can say, okay, well, this has probably converged. And if we see Z1, there are all these false values, there are probably some of them that are true. And if we do plt.imShow, it's going to show us the truth, literally and figuratively. So wherever you see white, it's 1 or true. Wherever you see black, it's 0. And you can see that some of these values have in fact converged. And you can already see the fractal-ish pattern here. So we can do this again and again for root 2 and root 3. And if we see this Z2, we see this. If we change it to Z3, we see that these values are the roots. So we kind of see these three regions where the roots have converged to. So now we're going to try to turn them into real fractals, which is also very straightforward. We're going to make an array and p.zeros, and we're going to make a shape of resolution by resolution. So 200 by 200, 300 by 300 in this case, and we're going to have 3 dimensions here. So it's really straightforward. This is what we're doing here, right? So we have a picture of 200 pixels, and by 200 pixels, let's say, and there are 3 dimensions, and because an image is represented by red, green, and blue RGB values, that's what we're going for here. So we're going to have a 200 by 200 by 3 array that's going to represent pixels, and each pixel is going to represent obviously 3 values: red, green, and blue. And while we're doing this, we're going to color each and every single one of these pixels based on the specific root this point converged to. So just like we have this 200 by 200 array, we also have another 200 by 200 array, right? And that array is a truth array. This one, Z1, Z2, and Z3. And they are going to tell us whether Z1 is going to tell me which points actually converged to root 1, and they will be true. Z2 is going to tell me which points actually converged to root 2, and those values will be true. So we're going to use that now. So for I in range NX, or resolution, in this case for I in range res, we're going to check if Z1 of I of j, if that is equal to true, I can just do this, but just to show you. If that is true, that means this is the point. The ij is the point where the z, or that point, has converged to root 1. So I'm going to color it in that way. Colors of 0, and we're going to do this for the second and third as well. Colors 1, colors 2. And if we continue now, we can do plt.imshow ARR, and we can see that we have our awesome fractals. And we can change the resolution as well here and rerun it. Like, we can change the resolution to maybe 600, which will take a long time, but it's worth it, I guess. And if we run it and we do plt.figure, let's say 12 by 12, hold up, fig size equals 12 by 12. We get this thing over here, and you can see that there are some points where there seems to be some sort of complexity, and they will repeat again and again. And I'm going to show you at the end of this video some easier ways to make these. I've also made another program that lets you use a user interface to do this. Now let's continue. What I'm going to show you now is how to use NumPy to declare these functions, so that you don't have to write these functions like a monkey, basically. I don't want to use these, I want to be able to declare these polynomials in a different way. And yeah, you can do that, and NumPy allows you to do that. So let's not be monkey. Yeah, that's the title. So to do that, we're going to define a polynomial using np.poly1d, and same way we did before with np.roots. So let's say 1, 0, 1, 0, 0, 0, minus 1. This is the coefficient of the constant. So it is the constant minus 1. Then x to the 1 has this coefficient, x to the 2 has this coefficient, so on and so forth. So 1, 2, 3, x to the 4 plus x to the 6. This is my polynomial. And another interesting thing is that I don't have to define fp, because I can use np.deriv to calculate the derivative. And this is also a polynomial. See, it's a poly1d. So it returns a polynomial, not an answer, obviously. And this is the derivative of this function. You can imagine x to the 6 is 6x to the 5, and x to the 4 is 4x to the 3. And it is x to the 3, it's 0, 1, 2, 3. And I can call in on any value and I'll get the derivative back. So that's what it is. Now I've already written some code here because it's basically using the same principles. So I'm not going to go into details. It's really just extending the same thing that we have written before to this. Just using p and p.deriv instead of those. And I've already written these, so I'm just copy pasting. We're doing the same thing here, but a little bit different because we want to account for as many roots there are. And there may be a better implementation for this. Do let me know. And now we can show a different root, basically, a different function, sorry. And we can change functions here, right? That old way was bad, so I can change it into this. And I'll get this. A little different function. I can change the resolution here. I guess is really, really bad. It'll take some time. It takes a lot of time to converge because there are more resolutions, and you can also improve your, I guess, convergence by having more having more iterations. And you can already see that it's looking already better. So that's all there is to Newton Fractals. Now I'm going to show you another application that I made, just following this code and turning it into something else that it wasn't, I guess. And I did this, let me show you. I did this in my free time. So let me show you. So I did this using PyQt. So new fractals.py is the thing. I'll share this with GitHub, so don't worry about that. And we'll open up. So this is the thing. And you can define your polynomial over here. So like 101. And this is the resolution. But it's really bad UI because you have to press enter for polynomial. So it's going to go and do its work, whatever it does. And you have to redraw. Come on, redraw. And you can change the resolution as well. Like turn it 400 and redraw. Yeah. So that's all there is to Newton Fractals. And yeah. I'll see you in the next one, I guess.